Hello and welcome. Today we're going to take a look at a topic in differential equations, which is the integrating factor, and it is one of my favorites. So our goal today is going to be to try to find a way to solve first order linear differential equations, and these are in the form y prime plus p of ty equals g of t. And we'll use our method to solve some examples. So ultimately, to solve, we want to get y equals. So we need to figure out how to handle this y prime, right? And we'll do that through integration. But that means we need to find a form that we can integrate, right? As it is now, we can't integrate. And this happens to be a nifty little trick that I think is quite impressive. So if we just look at the left-hand side of our equation, we have the form y prime plus p of ty. Now, if this is a derivative, we could integrate it, right? So the integral is the antiderivative, right? And so the derivative and the antiderivative are inverses. So if this y prime plus p of ty is equal to the derivative of some function q, say, then we could just integrate, right? We can integrate q prime and that would give us q. And so that's kind of what we want to figure out. How can we make this look like the derivative of some function? But how could that be, right? If we write this out in a different form, we really have d of y d of t plus p of ty, right? And in calculus, when we're integrating, we normally see something that looks more like f of x dx. And here, we've got this plus, right? This is really more like f of x plus d of x. And that's strange, right? That's not what we're used to seeing. So how can we possibly integrate this, or how could this possibly be the derivative of some function? Well, in come the clever mathematicians, right? And they say, wait a second, this is a weird form, but we've seen this before. Where have we seen this before? And of course, it's our product rule, right? Well, how does that happen? Well, if q of x is equal to the product of two functions, r of x and s of x, right? Then the derivative of q of x is the first function r of x times the derivative of the second, so s prime, plus the second function s times the derivative of the first r prime. And if we look at the form that we're actually working with, we have y prime and y, right? So we have our function plus something times the derivative of our function, which looks a lot like the product rule, right? So how can we kind of make this work so that this actually takes on the form of the product rule? Well, if we multiply by some function, we don't know what that is yet, but if we multiply by some function r of t to this whole expression here, we have r of t y prime, which looks a lot like r of x s prime, right? Plus, well, if our y and our s prime are what we're comparing here, then s would be our function, and here y is our function. So our function s of x would be y in instance, right? Plus y times p of t r of t. Well, that would be our r prime, right? So as long as the derivative of our function r that we're multiplying by is equal to p of t r of t, we have the product rule, right? And now that means that this function is the derivative of something, and we can integrate it to solve. But what is that function, right? So, okay, so we know if we multiply by some function r of t, we're going to get the product rule form, right? But we have that one caveat that the derivative has to be something specific. And so we need to find a function where the derivative is just that function, right? Because our derivative of r of t includes r of t in it, and that's not super common, right? So maybe we start looking at polynomials, and we look at the normal form of polynomials. Well, if we take the derivative, right, we get this lower degree polynomial, but it doesn't have our original f of x in there, right? Our original f of x, because we don't have an x to the nth in here, right, is not there. So a polynomial is not going to work. But what if we think of another common function, like a trig function, right? What if of our r of t that we multiply by, we have a trig function for that? Well, our trig functions are periodic, right? The derivative of sine is cosine. The derivative of cosine is negative sine. So we aren't getting that the derivative of sine has sine in it, right? And so that's not really going to work either. But we do actually know of a function, a special function, and this is one of its great properties, where the derivative of the function is simply the function, and that's our exponentials, right? If f of x is e to the ax, then the derivative of that is a times e to the ax, right? So the derivative of f of x is some constant a in this case times f of x, right? So if we have an exponential with just a constant, right, in our power, right, in our exponent, then we get this really nice form that is going to work with what we're trying to find. So let's look at this in action. So say we have this differential equation y prime is equal to 3 minus 2t minus 1/2 y. So first thing we want to do is group like variables. In other words, put this in standard form, right? We saw our standard form was y prime plus p of ty equals some g of t. So we're going to move all of our y's to one side, right? Next, we're going to multiply by our integrating factor. They're multiplied by our r of t so that we get this product rule form. Well, what's our r of t here? Well, our a in this case is going to have to be our 1/2, right? And so we'll have e to the 1/2 t, and we multiply that through the entire equation, right? And then does this work out? Yeah, right? Our r of t is e to the 1/2 t. So then our r prime of t is 1/2 e to the 1/2 t, right? So we have r of t times the derivative of y prime, derivative of y, right, y prime, plus the derivative of r of t plus our function y, our next function y, right? So this means that this left-hand side of this equation is the derivative of the product of the functions y and r of t, right? Because a product rule would say we take the first function y times the derivative of r of t, which is our y 1/2 e to the 1/2 t, plus our second function e to the 1/2 t times the derivative of y, which is our y prime. And so now since our left-hand side is the derivative of some function, we can integrate both sides, right? And the integral of a derivative is just going to give us that function. So this example, the fun actually comes in integrating the right side because we get to use a couple of different rules. So this is a good sort of brush up on integrating these types of functions. So when we integrate the left, we get the function y rt, the product, plus rc1, our constant of integration. And then on the right-hand side, I've distributed our e to the 1/2 t throughout. Now, using the linearity rules of calculus, we can separate this into two integrals, right? So our integral of e to the 1/2 t times the quantity of 3 minus 2t dt becomes 3 times the integral of e to the 1/2 t dt minus 2 times the integral of t e to the 1/2 t dt. And this is messy, right? This has got a lot of stuff going on. So let's start with substitution. And let's let u equal 1/2 t just to clean this up a little. So the derivative of u would then just be 1/2 dt. And if we multiply both sides of that by 2, we get 2 du is equal to dt. And so we can substitute this back in. And so now we have 3 times the integral of e to the u, right? So we replaced our u with 1/2 t. And then our dt is 2 du. So we have 2 du minus 2 times the integral. Well, we have t here. Well, remember, u is equal to 1/2 t. So multiplying that 2, right, by both sides, we get 2u is equal to t. So our 2u is substituting for our t, e to the u, and then again, our dt is 2 du. And so we can multiply all of these constants out and get that this is equal to 6 times the integral of e to the u du minus 8 times the integral of u e to the u du. All right, so now anytime we see that sort of multiplication, that t e to the t sort of situation, we know that that's going to be integration by parts, right? So we're going to use that formula, and that formula is defined as the integral of u dv is equal to uv minus the integral of v du. So we already substituted, so we had that u equals 1/2 t. And so we're going to keep that, so u is u, and then du is going to be du, right? Our dv becomes e to the u, and then integrating that, our v is just e to the u. right? So we're going to substitute this into the formula. And so our first integral is going to stay the same, 6 times the integral of e to the u du. And we're going to use our integration of parts on the next one. So we have minus 8 times the quantity uv. So that's u times e to the u minus the integral of v du. So that's going to be minus the integral of e to the u du. And now we've got something that we can integrate, right? So distributing our negative 8, we get 6 times the integral of e to the u du minus 8u e to the u plus 8 times the integral of e to the u. And we have these two integrals of e to the u, so that we can also combine, right? And so we can combine that. These are all of our steps here so far, but we can combine that 6 and that 8 to be 14. So we end up with negative 8u e to the u plus 14 times the integral of e to the u du. But of course, the integral of e to the u is just e to the u. So we get 14 times e to the u plus our integration constant, right? Now, our u, we got to throw back in, right, to what it was originally, which is our 1/2 t. So we plug that back into all of our u's, and we can simplify this as well as adding our constants, our integration constants together to get that y times r of t is equal to negative 4t e to the 1/2 t plus 14 e to the 1/2 t plus c. And then now what do? Well, remember, we want to solve for y, right? So since our r of t was e to the 1/2 t, we're going to divide both sides by that to get our final solution in terms of y. And so that gives us y equals negative 4t, right? Our e to the 1/2 t and our r of t cancel out, plus 14, again, they cancel out. And then don't forget, we also have to divide our constant, right, by e to the 1/2 t as well. Notice that that's in terms of t, right? That's a function in terms of t. So before, we could combine our constants because they were both constants. But here, our r of t is not a constant, so it doesn't just get absorbed into that kind of placeholder here. All right, so that's great. We solved this equation. We did what we want, but we sort of skipped over a big part there, right? Like we saw that it was plus 1/2, and we sort of knew what that was by our understanding of exponential functions. How do we do this in any case? So in that example, we found r of t easily, but what if we had something like ty prime plus y equals e to the t? Right? When we put this in standard form, what happens in front of our y, right? Our function r of t that's attached to our y is actually a function of t here in terms of that it's not a constant, right? It's not 1/2, now it's 1 over t. So how do we know what to multiply by, right? We know it's going to be an exponential, but how do we know what to multiply by in any case, right? In any of these cases, right? Well, this r of t is exactly what we call the integrating factor, right? That's what we're multiplying by. We're multiplying by this function that allows us to integrate, right? Because it creates the product rule for us. All right, so let's take a look at this function, f of x equals e to the x squared. Well, if we take the derivative of this, we get e to the x squared, because that's the beauty of our exponential functions. But then by the chain rule, we have to multiply by the derivative of the exponent, right? So we multiply by 2x. So generalizing this, right, the derivative of an exponential function raised to some p of t, right, is the derivative p prime of t, and then that exponential, again, e to the pt, right? So the antiderivative and the integral, again, are inverse operations. So to achieve this in any case, we need to make r of t e to the integral of p of t dt. Now remember, we want r prime of t to be p of t times r of t, right? Just like we see here, right? So here our derivative is f of x, and then we want this to be times our p of t, right? So our 2x is our p of t. So how do we do that? Well, that means our exponent has to be the integral of the function, right? Because then what happens, right? So this is the form that we want to get, right? R of t times y prime plus r prime of t times y, right? So let's look at what happens when we put in e to the integral of p of t dt in there for r of t. right? Well, we have the first function, r of t, which is e to the integral, right, times the derivative of the second, y prime, plus now we have the derivative of r of t. Well, what is that going to be? Well, we take the exponent, right, and we take the derivative of that. But the derivative of the integral is just going to give us p of t, right? And so that gives us exactly what we want. We have r of t y prime plus p of t r of t y. And if we go back to when we started, that's exactly what we wanted, right? We said that this will work as long as r prime of t is p of t r of t. And by making this exponent the integral of that p of t, that's exactly what we get. And now this is what's going to allow us to use this method with many, many different types of functions. So let's look at one more example that's a little bit more complicated where we don't just have a constant. So we have ty prime plus 2y equals 4t squared. So again, our first step, put this in standard form, right? And that gives us, we're dividing everything by t, that gives us y prime plus 2 over ty equals 4t, right? Of course, t cannot be 0. Next, we're going to multiply everything by our integrating factor, right? So since our p of t here is 2 over t, that's our standard form, right? Y prime plus p of ty, right? Then our integrating factor, using our formula that we found here, is e to the integral of 2 over t dt, right? Well, what's the integral of 2 over t? Well, that's just 2 times the natural log of t, right? And that gives us e to the natural log of t squared, using our properties of natural logs, right? So we can bring that power down or alternatively bring that power up. So we have 2 ln of t, we're bringing that power up to make the ln of t squared. And then e and the natural log are inverse functions, right? And so that means that this gives us t squared. And so that's our integrating factor that we're going to multiply everything by. So we multiply t squared times our entire equation. Now let's make sure that that works out, right? So if we multiply this out, we have our first function, right, is t squared. So we have t squared times the derivative of y plus y, it should be times the derivative of t squared, which is 2t, which is exactly what we get. So our left side is our product rule, and it's the derivative of the product of t squared and y. So our left side is the quantity t squared y prime, right? And so that means that we have t squared y prime is equal to 4t cubed, and we can integrate both sides. And when we integrate, because of the antiderivative and the derivative, we're just going to get t squared y plus our integration constant on the left. And then integrating a polynomial is pretty straightforward, right? So we get t squared y equals 4t to the 4th over 4. We've already combined our constants here, plus c. And then dividing by t squared, right? And simplifying, we get y is equal to t squared plus c over t squared. And now we've solved. We've solved this first order linear differential equation. We put it in terms of y. But sometimes you're going to be asked to find an explicit solution, right? Depending on what our c value is, we haven't really narrowed it down. We still have an infinite number of curves that this function can be. So if we're given an initial condition, such as y of 1 is equal to 1, right? Then our last step is to solve explicitly. So we found that y of t is equal to t squared plus c over t squared, right? So we have that when y is 1, t is 1. So we substitute that in, right? And we have 1 is equal to 1 squared plus c. And that means that c must be 0, right? And so if this is our initial value, y of 1 equals 1, then our explicit solution, that one curve that relates to the differential equation we're working with, is just y of t equals t squared. So the method of integrating factors is super clever, right? To look at that and say, wait, this looks like a product rule, and then figure out what function can we multiply it by, and saying, oh, but we've got to have that integral in the exponent, is really a lot of clever steps that turns into this super easy process that we can use to solve these types of problems, okay? It's basically that if we're given an equation in the form y prime plus p of ty equals g of t, we can utilize that product rule by multiplying the entire equation by the integrating factor, which we define as e to the integral of p of t dt. right? And from there, we're able to integrate both sides and solve, right? And we can solve this in both general form or to find an explicit solution for an initial value problem. So I hope that this was helpful. I hope that if you're familiar with the integrating factor method, but you never really looked at why it works, that this is sort of an aha moment, because really understanding why it works is very clever, it's very interesting, and it allows us to minimize our mistakes, like to check for that product rule and things like that when solving some of the more difficult first order linear differential equations. All right, thank you so much, and if you have any questions, please just let me know.